So in the last class we discussed what is a Bernoulli random variable, right? And yeah, we are done with the expected value and variance of a random variable, and we have seen the properties of expectation and as well as the variance, right? So let's recall what is a Bernoulli random variable. So we say a random variable x is Bernoulli when it takes only two possible outcomes. Two possible values. And we say an experiment is a Bernoulli random experiment if it involves in its outcomes, if it involves either success or failure. If you have just success or failure in your random experiment, then we say such an experiment is a Bernoulli experiment. And performing that experiment once, we call it as a Bernoulli trial. So when you perform a Bernoulli trial, there are only two things. Either you will get success or failure. That's it. So that's what we call a Bernoulli trial. And a Bernoulli random variable which takes only two possible values. So it depends on how you are going to assign. For a success you can assign 1, and for a failure you can assign 0. And okay, if you don't like 1 and 0, you can take as any other numbers. For a success you can assign 10, for failure you can assign 5. Kind of, we have seen when you play a game, like if you win, you'll get 10 rupees, and if you lose, you'll get negative 5 rupees. So in that case, for a random variable, you are assigning the value 5 for a success and 10 for a success and negative 5 for a failure. So this is how. So it's not that it's compulsorily should take 0 and 1, but mostly in most of the cases we prefer 0 and 1. So now if you look at the probability mass function of Bernoulli random variable, that is P of x, you could see that is so if you know the probability of getting success is P, then this is P when x is equal to 1, and it is 1 minus P, and we are going to denote that with Q. So let me write Q here, Q when x equal to 0, and it is 0 otherwise. At rest of the values it is defined to be 0. You can see what is Q here, where Q is nothing but 1 minus P. This is the relation. And you can write it in this way as well. Probability that P of x, you can simply write it as this is P power x into 1 minus P whole power 1 minus x. This is what for x equal to 0, 1, and it is 0 otherwise. You see, when you plug in 0, you'll get 1 minus P. When you plug in 1, you get P. The same thing, the same function, we have expressed it in this way. So this is the probability mass function of a Bernoulli random variable. Now, we are going to perform these Bernoulli trials n number of times. Let's assume that we performed n Bernoulli trials. Now this time my interest is to see how many success occurred when I perform n Bernoulli trials. Okay, let's assume that n Bernoulli trials are performed. Now I'm going to define a random variable x here that counts number of success occurred in n independent Bernoulli trials. Let's assume that one trial which is not going to affect the next trial. Like when you toss a coin, if the first outcome is head and that do not decide the second outcome. That may be head or tail, we are not sure about it. So that trial is independent there. One trial is independent of other trial. Okay, so number of success occurred in n independent trials, independent Bernoulli trials. So this is what we'd like to see. Okay, so for example, let's take this case. If I toss a coin, let's assume we are tossing a coin for 3 times. Right? So for example, let me take this experiment. My experiment is to tossing a coin for 3 times. Tossing a coin for 3 times. So, and tossing a coin once, you can take it as a Bernoulli trial. Why? Because either it will give you head or tail. Only two possible outcomes. Okay. So here, success, I mean getting head. Let me take getting head as a success. So now let me define my x. X is a random variable which counts the number of heads occurred. So the number of heads occurred. Now what are the possible values of x here? There may be 0, no head occurs, or 1, or 2, or 3. Now I'd like to know what is the probability that x equal to 0. What is the probability that x equal to 0? Can you tell me?
One, sir.
1. I think you are saying that there is only one favorable outcome. So 1 out of, you may say, 2 cube. Yeah, this is correct. Okay, now let me change my problem from 3 times to 30 times. This time I'd like to change it from 3 times to 30 times. I'm tossing a coin for 30 times. Now x counts the number of heads occurred. Now the possible values are 0, 1, 2, 3, 4 and so on, 29 and 30. These are the possible values of x. Now you tell me what is the probability that x equal to 0. And next, what is the probability that x equal to 15. And also what is the probability that x equal to 25. See, for x equal to 0, it is easy to calculate. Why? Because every time we need a tail, isn't it? So every time we need a tail. So the first time the chance of getting tail is 1 by 2, and the second time the chance of getting tail is 1 by 2, and so on. For the last time the chance of getting tail is 1 by 2. So it is totally 1 by 2 whole to the power of 30. This is how we can simply write. So next, for 15, can I say the same thing? X equal to 15. It means out of these 30 trials, you perform 30 trials, right? Out of these, you want 15 of them to be heads, and remaining 15, we want them to be tails. So now the question is, where should I have these 15 heads? Is it that the first 15 places, or the last 15 places, or the middle 15 places, or any random 15 places? So we should count all of them, right? Not just one. See, when x equal to 0, there is no issue. Everywhere you got a tail. So there is no issue. There is only one way you can do that. But when you want 15 heads, so it's not just the one way. There are many ways you can do that. How we can calculate it this way, that is 30 factorial by 15 factorial into 15 factorial. That many number of outcomes you have. Okay, so now we should count all of them. So how many of them are there? We counted this way, 30 factorial by 15 factorial into 15 factorial. Of course, you can see it this way. This is 30 factorial by 15 factorial into 30 minus 15 factorial. And this can be written as 13 choose 15. Isn't it? So there are 30 places. Out of these 30 places, I need to choose 15 places. And at these 15 places, we keep head. That's it. And rest of the 15 places we keep tails. So now the probability that x equal to 15 is going to be 30 choose 15, okay, into how many success we got? Total 15 number of success, so 1 by 2 power 15. And how many failures? Total 30 minus 15 failures. In other words, you can simply write 15 failures. Isn't it? So this is the chance that you are going to get 15 heads. Similarly, if you want to calculate it for 25 heads, probability that x is equal to 25. So you just need to select the places, 25 places where you want to have success into, now how many success you got? 25 success, and the rest of them are failures. Of course, you can directly write 1 by 2 power 30, no issue. So now this is the probability mass function for x. And let me rewrite it. Probability that x equal to I, that's going to be 30 choose I into, this is 1 by 2, that is probability of getting success, power I, into 1 minus 1 by 2, that is probability of getting failure, whole to the power of n minus n. So this is the formula we got it, where I is equal to 0, 1, 2 and so on up to 30. Okay. So this is the probability mass function for our random variable. Okay. Now this time let me take another random experiment. So I'm just taking some random experiment that involves either getting success or failures. So let me assume that n independent Bernoulli trials are performed. Okay, and here the probability of getting success is P. Let me name it. That's equal to P, whereas the probability of getting failure that's equal to 1 minus P. Okay, so this must be a small p, it's not that capital. And we denote 1 minus P with Q. So now let me define my random variable x that counts the number of success occurred. Right. So now what are the possible values of x? So x can take the values 0, 1, 2 up to n. Why? Because we are performing n trials. It is possible that at max n success can occur, and it is possible that no success can occur. So these are the possible values of x. Now the question is, what is the probability that x is equal to I? This is what we'd like to know. Now it is same as the previous question. There are n places. Out of these n places, we want I success. We want I places in which success occurs and the rest of the places failure occurs. So first of all, let us select the places where you want the success, that is what n choose I, into how many success you want, I number of success, and the probability of getting success is p. Okay, so the probability of getting success is p, so p power I into 1 minus p whole power n minus I. See, for example, when you're performing an experiment for 4 times, let's say this is how it occurred: success, failure, success, and failure. So now, if you look at the probability of getting this element, so the probability of getting success is p, failure is q, success is p, failure is q. So this one you can express it as p square into q square. Suppose if you have this, that is success, failure, success, and success. So now the chance of getting this kind of element is, first you want a success, next you want a failure, success, and success. So this is p cube into q. Okay, so if you want to know how many elements are there in which there are exactly 3 success when you perform a random experiment for 4 times, if you observe that there are actually 4 choose 3, this many number of such elements are there in which 3 success occurs, 1 failure occurs. Okay. So now this is the probability mass function of this random variable. Probability mass function of this random variable, where I equal to 0, 1, 2, 3 and so on up to n. And one interesting thing here is, if you look at this expression is looking like this: n choose I into x power I into y power n minus I. Do you agree? See, since I am taking 1 minus p is equal to q, okay, let me rewrite this guy. So this one can be written as n choose I into p power I into 1 minus p, we are denoting it as q, so q power n minus I. Now it is in this form, that is n choose I into x power I into y power n minus I. And do you remember, this is what exactly a term in the binomial expansion? So now this is exactly a term in the binomial expansion, isn't it? Now the probability mass function, it resembles the terms in the binomial expansion. Okay, since the probability mass function resembles this binomial expansion, so we call this random variable x to be a binomial random variable. Why? Because its probability mass function has the terms which are there in the binomial expansion. Okay, I hope you know what is the binomial expansion. The binomial expansion of x plus y. So let me write it here: x plus y whole power n. So what is the binomial expansion? Summation I equal to 0 to n, that is n choose I into x power I into y power n minus I. So this is the binomial expansion, right?